You are watching the 4.1 Introduction to Exponential Functions video notes. In this unit, we are going to talk all about exponential functions. So last unit we talked about linear. So we looked at a bunch of lines. And the biggest thing that you should have taken away from the linear functions unit is that there was always a starting point, which was the y-intercept, and there was some type of constant pattern of either addition or subtraction, and we called that the slope. So exponential functions work in a similar way, but there obviously are some differences because it's a completely different type of function. So let's begin. Let's look at some of the exercises here and make the connections between linear functions and exponentials. In exercise 1, it says use the figures below to answer the following questions about the number of black triangles. So in part A, it says to make a table of this situation. It looks like all we need to do is record and count. In figure 1, there are 3 black triangles. In 2, there's 3, 6, 9. In figure 3, it looks like there's 3, 6, 9, 12, 15, 18, 21, 24, 27. Oh my goodness. All right, figure 4, take a minute, count all of those. You should end up getting 81 triangles. Some of you may have developed a pattern already because you didn't want to count up all of those tiny little black triangles, which is great. So looking at the patterns is something that we are going to address down below. So in part B, it says, what patterns do you notice is happening with the number of black triangles? So what we're trying to do here is find some type of pattern. They're telling us there is a pattern to get from here to there to there. Obviously, figure 1, 2, 3, 4, that's going up at a constant rate. We're just counting by ones. Now, typically, we might say, oh, 3 plus 6 is 9. But is 9 plus 6 27? The answer is no. So let's get a little bit more creative. 3 times 3 is 9, but is 9 times 3 27? Sure is. How about 27 times 3? Is that 81? It definitely is. So what pattern do we notice? We're multiplying by 3. So C says, how many black triangles do you think there would be in figure 5? Well, I think for me, what I'd like to do is count all the way up to figure 5. But maybe instead of drawing the actual picture, we can just take 81 and now multiply 81 times 3. 81 times 3 would be 243. That would be awful to draw, so it's a good thing we found that pattern. D. How do you know this pattern is not linear? Well, in order for something to be linear, a line always has a constant slope. So we're constantly adding or subtracting something as we go down the table. So we know it's not linear because there is not something that's being added or subtracted every single time. And an even better way to say this is the average rate of change, aka the slope, is not constant. So we added 6, and then we added however many that would be, and then we added a different number every single time. So I just wanted to show that in red up here is that we added 6, then we added 18, then we added 54, so the average rate of change is not constant. This is a very big concept that we are going to talk about for this entire unit. Moving on to part E, it wants us to model this with the before now next rule. And it also reminds us that we have to start or state the first term. So the first term, let's do this first. So the first term is 3. This is a 0.13 in our table or on the graph. And let's talk about how to get to the now. Or maybe some of you might say, you know what? Why can't we write this as the next? We could do it either way. Let's just leave next because I think that's where most of our brains head towards. So how do we get to the next term? Well, we look at the now, and what do we do with it? Well, we don't add anything to it this time. We are multiplying it by 3. So this is different than an arithmetic sequence because we are now multiplying. This is what we call maybe a geometric type sequence. Now F says, can you write a function that models this situation? Well, this is pretty interesting because don't we typically have an initial value starting at 0? So maybe we need to do that. Maybe we need to go all the way back here to our initial value. But how would I do that? Obviously 1 minus 0 is 1, but since I was multiplying to the right, how can I go backwards? I need to divide by 3, and 3 divided by 3 is 1. So I technically, let's use function notation, f of x, and f of x would be the number of black triangles, started out at 1. And usually in a linear equation, we would start adding repeated addition that would be modeled using multiplying. But here we are showing repeated multiplication. So how can we show multiplying by 3 over and over and over and over and over again? So it looks like we would have a big multiplication problem that looked like this. So 3 times 3 times 3 times 3. Can't we model that as 3 to some power? So we're multiplying by 3 over and over and over again. Let's say x times whatever figure this would be. And if you're not sure, we can go back and check. So what if I'm on step 2? I put in 2, 3 squared is 3 times 3, which is 9, times 1 is still 9. Yay, that worked. 3 to the 4th power. 3 to the 4th power is 81, times 1, still 81. So that rule is working out great. So now we need to take this just one last step further and use this rule, f of x is equal to 1 times 3 to the x, to figure out how many triangles there would be in figure 20. Well, we said that figure is really our x value. So it looks like we need to input the x value of 20. And let's see what we get out. Go ahead and multiply that on your calculator. When you multiply it, you end up getting over 3 billion triangles. So obviously, we would definitely need a rule to help us because no one is going to be drawing 3 billion triangles. All right, let's take a look at exercise 2. We are looking at the exponential f of x is equal to the x. And they want you to complete the table of values below. It looks like they did something for us, but what we're doing is just a bunch of substituting. So for 0, it would be 2 to the 0. For 1, 2 to the 1st, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and on the other side, 2 to the negative 2nd, 2 to the negative 3rd, 2 to the negative 4th. We're just substituting in whatever input, we're inputting the x, and now we need to get out the y. Take a minute, pause the video, and complete your table. Use your graphing calculator. So here is a completed table of values. It's very easy to see that, well, it kind of makes sense. Every time we add a power, we're just multiplying yet again by 2. So some people might say, wait a minute, why is 2 to the 0 1? Well, if we multiply straight through, the opposite of multiplying, if we go backwards, is dividing by 2. That's right. So dividing by 2, every single step of the way, 16 divided by 2 is 8, divided by another 2 is 4, 2 divided by 2 is 1. 1 divided by 2 is, 1/2. That's where all of those fractions come from. We're just dividing by 2. So even though we have negative exponents, we are not getting negative numbers. So negative inputs are not negative, negative, so they're not negative outputs. What are they instead? They're fractions. So taking a look at exercise number 3, this is a continuation of exercise number 2. It's asking us which of the following is not equivalent, so not equivalent to 5 to the negative second power. Well, 5 to the negative second power, we know from exercise 2 that it becomes a fraction. And the fraction follows a very specific rule. It's always going to be 1 over whatever this is, but to a positive power. And we know that 5 times 5 is 25. So answer choice 3 is correct, so we got to cross that off. Answer choice 1 is correct, so we have to cross that off. We also should know in our calculator that 1 divided by 25 is 0.04, and obviously if we just notice that in number 3, 1 over 25 possibly cannot be the same as 1/10. Moving on to exercise 4, we are given a new exponential function. This one is slightly more complicated because there's actually an 8 out in front. So really what is happening is that we're taking the parent function 2 to the x and we're multiplying it by 8 every single time. We need to complete the table of values below, but at the same point in time, at the end, we'll verify using our calculators. Let's show our substitution. So here we'll have 8 times 2 to the negative 5th, and so on and so forth. Take a minute, show your work for the rest of this table, so you can pause the video. So here's what it looks like after we show the work of the substitution. Remember, we're just replacing x with all of the input values. Next, I would like for you to fill in the f of x, the output, and you can use your calculator to do this. Here is a completed table of values. It may not, or it may come as a surprise that there's a pattern yet again. And that pattern happens to be not the slope in like what we would see in a linear equation, but the multiplier. So how are we getting through the table? Well, we're multiplying by 2 to get from one step to the next, as long as our x values are going in order, one right after another in a consecutive order. All right, B wants us to evaluate each of the following functions and indicate what point must lie on the graph. Well, check it out. We have all of these inputs. Remember, this is our input, this is our output, whatever that is. So if we input 2, we get out 32. So what that indicates to me is the point 2, 32 will lie on the graph. At 0, we get out 8. So this, interesting. This point here, I wonder why that's in bold. This is the y-intercept. And look at your equation. Do you see anything interesting about 8? Well, it looks like we have that 8 hanging out in front here. I wonder if that will happen every time. Something to think about. The point -1, we get out 4, and that is a point -1, 4. If we move down to C, D, and E, it asks us to find the average rate of change of the function, and it gives us 1 and 2 different intervals for both C and D. So let's take a minute to do that. You know what I like to see whenever we talk about average rate of change. Hopefully all of you have already put a table on the board without talking to me. In C, they gave us the x value of -1 and 0, which we can easily pull the y values from up above. So -1, 4, and 0, 8. If I find the average rate of change, I just need to see how did 4 become 8? Well, we added 4. And how did negative 1 become 0? We added 1. So my average rate of change is 4 over 1, which is just 4. If we do the same thing for D, well, they didn't give us the same interval, but they sure gave us the same direction to find the average rate of change. So make another table. They want the x values from 1 to 2 again. And up in our table, we have the nice outputs. 1 is 16, 2 is 32. So figure out how the y's changed. We added 16. How did the x's change? We added 1. So 16 over 1, what do we notice about the average rate of change? It's not the same, so therefore this is not a linear function, which is what part E asks us. In E, we should say the average rate of change is not constant, so this is not linear. All right, let's jump back to our graphing calculator. We first need to graph our function 8 times 2, and I need to raise this to the x power, so I have to use my caret key. If I hit enter, this is what we're looking at. So we're looking at an exponential function, but down in part F, it's telling us to change the window. Let's take a minute to do that. This number should be 4. That didn't work. Let me try that one more time. 4. And we'll tab to get to the next. That needs to be negative 10. Tab to get to the next. And this is all review. And instead of 6.67, we need to go all the way up to 130. Now we have a slightly better picture of our exponential function. And it says to just sketch it so we don't have to go crazy with plotting a bunch of points, but it does, however, tell us to plot and label the y-intercept, which we know from up above to be 0, 8.